All right, so we're going to start looking at chapter 2 today. So to do that, we're going to look at a lesson. I'm going to try and walk through it in Paint. Just keep in mind that doing the best we can with the technology available. So we may hit some glitches, and that's okay. We'll just kind of work through them as we go here. So the first thing we're going to look at in chapter 2 is going to be basic just functions and their graphs. So when we look at functions and their graphs, what we're looking at is first, is something a function, and how do we tell, and then what does that look like? So function. It's probably not you, Drew. It's probably that the audio is just of low quality. That's one of the things that I want to figure out is whether it's just like impossible to do in this format, but my guess is it's probably just pretty bad. Yeah. So we're going to give it our all. I'm going to record this session. So basically just keep in mind that like this is a trial run. Do the best we can. If it works out great. And if not, it'll just kind of confirm what I thought before. So looking at functions and their graphs here, I can have one missile shoot to one target, and that's how I kind of want to think about functions. So I think about functions in terms of missiles, one missile to one target. Now I can have a different missile go to the same target, but I cannot have one missile go to two targets, okay? So no splitting here. And what that means is that I can have one input to one output. I can repeat the outputs, but I cannot repeat the inputs. So here I have 0 goes to 1. That looks good. 1 goes to -1. That looks good. -2 goes to 0. That looks good. 3 goes to 0. And then, hey, wait a second. We already had a 1 goes to -1. Why do I now have a 1 goes to 2? And what that looks like on the graph is this little bit right here. So when we look at this, we say it does not pass the vertical line test, right? This is one missile, two targets. This is the thing that we cannot have. So this is not a function because this x1 value is paired up to two y values, both -1 and 2. If I were just to graph a super quick version of something, as long as it looks like it passed the vertical line test, I'm good to go. So again, I have multiple y's that get repeated here. So say, for example, I drew a line through like this. They all have the same y value here, but each of them has a unique x value that brings me there. So this is a function, but this would not be, right? So if I turn this into a graph like that, we would see our vertical line test is broken in multiple places. For slope and rate of change, we just want to look at what our slope formula is. Our slope formula is right here. It's the difference in our y's over the difference in our x's. And the reason for that is that slope is rise. Oh, the handwriting here, top quality. Doing it with a mouse, folks. Next level. Here we go. Is rise over run. So when I'm looking at rise over run, the rise is the vertical portion, and that is going to be the y thing. The bottom is going to be the horizontal portion, and that's going to be the x thing. Now, it can be written as y2 minus y2 minus x1. It can also be written as y1 minus y2 over x1 minus x2. It will give us the exact same answer. We'll basically just have a positive result in one, and then the other one, it'll just be negative, negative, so it'll end up canceling off, or vice versa, 1 and 1, 1 and the other. So when we're looking at this thing, we're basically saying, okay, how can I figure out what the slope is? If I've got 2 points, how do I know which one is like the x1 and which one's the x2? And the way that we do that, or excuse me, x1, y1, x2, y2, and how do we do that? And the answer is it doesn't matter at all. So when we're looking at these 2 points, just in this example here, we're going to call this one the x1 and y1, and we're going to call this one the x2 and y2. The important thing is just not to crisscross them. Other than that, we can't screw up. So looking at this here, I'm just going to circle the values we've got. So again, we're using x2 minus x1. So this is our little green value there. Blue value here, which is our -3. And then we have 4. And we have subtract off 0. So hopefully I'm not covering it up too much here. We got 4 minus 0 coming from the y2 minus the y1, all divided by, now here I have -3 minus my 5, which is the x2 minus x1. It simplifies from 4 over -8 to -1/2. So my slope here is -1/2. Now in terms of what -1/2 looks like as a slope, just in general, means I'm going to be going one of two things. I'm going to be either doing -1 over 2, or I'm doing 1 over -2. And I'll be very specific about when we talk about this thing. I don't want to say over, right? I want to say to the left or to the right, but I don't want to say over because I don't know what that means. So what the actual translation of this is I'm going to go down 1, and I'm going to go right 2. If I look at this one, I'm going to go up 1, and I'm going to go left 2. So when I'm looking at this, no matter where I am, so this can end up looking like this, or like this, or like this, right? I'm not sure what the y-intercept is, but it's always going to be the same. I'm going to be going up and to the left or down and to the right. For quick graphs of linear equations here, this is just our whole y equals mx plus b, knowing the slope and the intercept. Here we have our y, this is our output value. Here's our x, which is our input value. We have our slope here, which is -3. And then we have our y-intercept, which is the b value. So when I'm looking at this, I should be able to very quickly and easily see where this thing is going to start and then what I'm going to do with it. So it always starts at the b value. If I don't see anything here, so say for example, I had a y equals 2x. Do I have a b value? Yeah, I do. My b value just happens to be 0. So if we don't see the b, just know that b is 0. What if I don't see an m, right? So what if I have something that looks like this? Y equals x plus 2. I don't see an m value. What does that mean my m is? My m here is 1. So again, we still have these values. It's just we don't say plus 0 and we don't say 1 times whatever. So now looking at this one here, I know that my graph is going to start at 1, and this is a y-intercept, so it's going to be on the y-axis. So this is the up-down line here. This point, 0, 1, is where I start, right? If I plug in 0 into this equation, what happens? -3 times 0 gives me 0, plus 1 gives me 1. So when I plug in 0, y value is 1, hence the point, 0, 1. What do I do? What is my slope? So I'll write out the slope just to make it explicitly clear. I can write it out one of two ways. I can write out -3 over 1, or I can write out 3 over -1. This one is telling me to go down 3, right 1. This one's telling me to go up 3, left 1. So I'd put a point out like that, and put a point out like that, and then I would just connect my line across like this. Now I have just graphed this function here. If I have a equation in the format that looks more like this, you can just find your x-intercept and your y-intercept and graph like that, but you can also convert this into slope-intercept form. To do so by itself, so to get y by itself here, I would say let's just subtract off 4x. So now I have -3y equals -4x plus 12. Next move is to divide by -3. So my y value equals 4/3 x minus 4. And we see we start at 0, -4. We will go up 4, 1, 2, 3, 4, and to the right 3, 1, 2, 3. Oh, hey, we just graphed the exact same line, just doing it in a slightly different way. I left myself some space to do this, but hopefully it wasn't too confusing up here. So we'll just make up one more example here. Say y equals 2x minus 3. My b value is my -3. My slope m value is 2. So it means I'm going to start at -3. My slope tells me to go up to right 1 or down to left 1. From there, I graph my line. Pretty close. There we go. Whatever. I mean, it's not going to be perfect in terms of my line, but there we go. And we're good to go. Writing equations of lines. So if we're looking to write an equation for a line, the thing we need first is the slope, and then we can use that to find the y-intercept, and from there we can write the equation. So the first way that you'll see it is the easiest, which is that if we're just given the slope and the y-intercept. So if I told you the slope is 2 and the y-intercept, the b value is -3, this should be the easiest problem you've ever seen in your life. It's just y equals mx plus b, plug the values in, and there's our equation. So there's really nothing we're doing here other than just filling those values in. Point slope form is a little bit more interesting. So when we do point slope form, what this is saying is basically we're taking the slope that we know, and we're taking one of the points that we know, and we're plugging it in to solve. So here, if I'm given a slope of 2, and I know that this thing is going to have this point 2, 1, then this is the point I'm going to use along with the slope here. Oops, let's do it in orange. Using this point, using this slope, I'm going to write out what slope form looks like. So it's y minus y1 equals m times x minus x1. So the important thing to note here is that the x1 and the y1 are actual values. So those are the numbers coming from the point we were given. So we were given this point, 2, 1. So my x1 value is 2, and my y1 value is 1. I'm just going to fill in these, carry it down. My slope here, we were told, was 2. So that's where I'm going to include my slope. I'll do it in green so it's sticking out a little bit more clearly for us. Here's my 2 times all the stuff I had before. This x remains an x, right? We're looking for an equation, so we still need to keep our x and our y in this equation. My last step here is just going to do some solving so I can get everything on one side and get the y by itself. So I'm going to add 1. And I'm also going to do my distribution here. So my distribution here is going to turn this into 2x minus 4. And with the 2x minus 4, just know that I'm adding 1. So I'm going to add 1 here as well. So my final equation should look like y equals 2x minus 3. For the last one here, if we're given 2 points, the only additional thing that we're doing is that we're going to take this and generate a slope based on the 2 points. And we do that using our slope formula. So again, we're going to do x1 minus x2 on the bottom, y1 minus y2 on the top, and then we're going to find out the slope for this thing. So let's do our m value equals, so I'm just going to do it as y2 minus y1 like this. So I'm going to do 1 subtract -3. And I'm going to do the same thing for my x's. So directionally, I'm going to do it like this. So 2 minus 0. 1 minus a -3 gives me 4. Over 2 minus 0 is 2. So my slope here is 2. So now that I know my slope is 2, I'm going to then plug in a point and go from there. Now I'm not going to plug in the point and go from there because guess what? That's what we just did, right? My slope here was 2, and it included this point 2, 1. So these are actually the same equation. It's just the one additional step we would need if I just gave you 2 points. We're not going to do a ton with correlation and best fitting lines. When we look at these, basically we're looking at, is there a positive or negative correlation? And is there a correlation in the first place? If I were trying to generate an equation for this thing, I would try and set it up. So here's my first point. And again, I'm just selecting one. I'm going to say, here's my last point. Again, I'm just selecting one. So let's say, for example, I was using this and I was using this. I would set it up so I'm using the 2 points that I've got to find a slope. Again, they've slightly adjusted the point here. They're like guessing where this is going to land. At this level, where we're not doing like real correlation stuff, just grabbing 2 points that look pretty close is all we'll be doing. And we're not even going to do a ton of this stuff, but we should at least know what it is. So then from here, I'm going to say, okay, find my slope. This ends up being 5 in this example here. From there, we're going to do exactly what we just did up here. So jumping back up for a second, we're now using the slope to solve, and we've got at least one of the known points. When we're choosing the point we're going to use, it really doesn't matter which one. So you can use this point or this point and plug it back in. It's not going to make a difference either way. When we see the different types of correlation, we want to know how to call them out. So we'll do the first one here in green. If I see something that looks like this, more or less, we see this as a positive correlation. If I see something that looks something like this, we would say it has a negative correlation. And if I saw something that looked like this, we would say there is no correlation. Looking at linear inequalities in 2 variables. So here, the only thing different about what we are doing now versus what we were doing at the beginning when we were looking at graphing these things is that now it's an inequality. So instead of it just being equal to, which would generate a line for us, we're going to have a line and then an entire section which is being shaded. So basically this is the scenario where we're saying, okay, it's anything bigger than this or anything less than this. So when we're graphing this, we're going to basically treat it like we were just graphing it normally. I'm going to rewrite so we have a little bit more space down here. I'm going to call this thing y is what, less than x plus 2. So my m value here is 1. My b value here is 2. When I go to graph this thing, I start at b. M value is 1. That means I go up 1, right 1, or down 1, left 1. So I'm going to plot out a couple points here. Now I'm going to draw my line. Now in drawing the line, I'm going to look at whatever my inequality symbol is. My inequality symbol here is strictly less than, strictly less than. So what that means is it's going to end up being a dotted line. If this was less than or equal to, then it would be a solid bold line here. Okay, so just keep in mind, if it has that little line underneath, it means less than or equal to, and that's how it can actually be the line. So that's why we do a bold line. If it's just less than or just greater than, it's a dotted line. So now I'm going to draw this thing in. It'll look something like that. My last step here is going to be to do the shading. Now there's a trick for the shading. If y is less than something, it means I'm going to shade below. So imagine there is a big sun shining from right here, right? The sun is shining from above. If it's above, I'm going to hit the stuff up here. If it's below, I'm going to hit the stuff down here. So below is going to get shaded all down here. And I just do it with a little squiggle like that. And we can test this as well. So what's one point that's definitely in this region? Well, I love plugging in easy points. 0, 0 looks to be in that region. I wouldn't want to pick something like 0, 2 because that's right on the line. It's not going to help me determine where I'm shading. So this is just to check to see that my shading is correct. So I'm going to take 0, 0 and plug it into this equation here. So now what I'm saying is 0 less than 0 plus 2. Yeah, last time I checked, 0 was less than 2. So check, this works. And any point I pick in here is going to work. So if I picked 3, 1, or if I picked -2, -3, all of these points are going to work. If I picked a point outside of this range of shaded values, so say I picked like 0, 4. If I try to plug in 0, 4, what's going to happen? I would get 4 less than 0 plus 2. Is 4 less than 2? No, it's not. That's why we do not shade up here. Do one more example. We'll do y is greater than or equal to negative 2x minus 1. So when I'm looking here, I'm saying, okay, my b value is negative 1. I'm going to start right here. I have a slope of negative 2, so I can go down 2, right 1, down 2, right 1, or I could go up 2, left 1, up 2, left 1. In terms of whether this thing is shaded or bold, this is going to be bold because it's greater than or equal to. I'm going to draw my line bold right through there. And then from here, where am I going to shade? Here I have y is greater than equal to this thing. So if it's greater than, I'm going to be shading above. So shade above. Could we check our work? Yeah, the 0, 0 point looks like a good spot to test it out. So if I took 0, 0 and plugged it in, is 0 greater than negative 2 times 0, which is 0, minus 1? Yeah, 0 is definitely greater than or equal to negative 1. Last time I checked, so we're good to go. Piecewise functions are the thing that is going to give people probably the most difficulty here. You guys should have done these before, but it always kind of seems to be the hardest thing from chapter 2. That and then the runner-up would be the absolute value stuff. So in a piecewise function, the way that I describe it is we're going to get some notation that looks like this, right? It's either going to be y equals or f of x equals, right? So it looks like one of these two things, they mean the same. F of x just meaning the function of. This is kind of getting phased out, so you should see it like this more often, but whatever. Then we see this bracket here, and then we get a bunch of rules. Now the rules tell me, do this when this, okay? So I'm going to do an example. It's got nothing to do with math, but it'll help us understand this. So I'm going to say we wear a coat if temp is less than 40. Might need to adjust my text down a smidge here. Okay, so I'm going to say we wear a coat if the temp is less than 40. And I'm going to say no coat if the temp is, and now here it's just tough for me to insert the greater than or equal to, so I'll write the little line underneath. Greater than or equal to 40. So let's do my little sneaky line there. There we go. So here's my piecewise function, okay? This is the thing that I'm doing. I'm wearing a coat or not wearing a coat dependent on the temperature. So if it's less than 40, I'm wearing a coat. If it's greater than or equal to 40, I will not wear a coat. So when we're doing piecewise functions, these functions here are just going to be things that we could graph. So looking at this first example, 2x minus 1, could we do some stuff with that? We absolutely could, okay? 2x minus 1, for the most part, I'm going to do a very, very quick sketch. So I'm going to start at minus 1, and I go up to right 1, down to left 1, right? So this is my sketch of, I should do it in another color. This is my super quick sketch of that graph, okay? And then I've got 3x plus 1. So my 3x plus 1 is going to start up 1, and it's an even steeper slope. So it's going to look, you know, something like that. So again, super, super quick sketches here. Don't take it too seriously. Now, the thing that is different between these two is that I only do the green thing if my x value is less than or equal to 1. So basically, I've got this rule change happening right at 1 here. I'm going to say this is x equals 1. So at this line, I swap between what I'm doing. I do the green thing to the left, and I do the blue thing to the right. So what I'm going to end up doing is getting rid of this green stuff to the right here. This is now gone. The blue stuff, I'm going to get rid of to the left here. That is now gone. My final graph should just look like blue going up to the right and green going down to the left. And it's kind of broken off like that. Now, the green, since it is, assuming x is less than or equal to, we'll have a filled in circle here. And the blue, because it is strictly greater than 1, we'll have an open circle right there. I'm exaggerating extreme here, but you get the point. Let's do an example of just plugging in values, okay? So we're going to evaluate a few values. The first one we're going to look at is f of x when x is 0, okay? So which of these two buckets am I going to be? I've got a red bucket right here, and I have a green bucket right here. Now the red bucket is what I would do if x is less than 2. Is x less than 2 here? Absolutely is. So I'm going to take it and plug it into the red bucket. So I should be doing x plus 2. Well, x is 0. 0 plus 2 gives me 0. That's how we get that answer there. Let's do the next one. So looking at the next one here, x equals 2. Keep in mind, this is strictly less than. So for x is greater than or equal to 2, I'm doing the green thing. Green thing says x equals 1, x plus 1. 2 times 2 is 4, plus 1 is 5. Check. Last one here, x equals 4. 4 is greater than or equal to 2. So this is going to be another green one here. When I plug this in, 4 times 2 is 8, plus 1 is 9. Check. So that's how we evaluate our piecewise function. For the graphing part, this is basically exactly what I said before. This is what we graph when our x is less than 1. This is what we graph when our x is greater than or equal to 1. So the first part here, I'm just going to highlight as the red bucket. I'm going to highlight this one as our green bucket. Red bucket stuff happens when x is less than 1. This is where this thing is going to get separated, okay? This line at x equals 1. For all that stuff, it's going to be strictly less than. So I'm going to have an open circle here, and I'm going to be going down to the left, just trying to trace over this already existing graph here. So again, starting at 3/2, which is right about there, I'm going to be going up 1 to the right 2, or down 1 to the left 2. So that's this line right here. Then for my green bucket, I'm going to be starting at 3. So again, the green rule starts engaging here, and it's for greater than or equal to. So now I've got a filled in circle. It's okay to have an open circle and a filled in circle sharing the same point. They don't always do that. Most of the time they don't, but when they do, that's okay. So now this is going down to the right like this because my slope is -1. So again, if I start at 3, 1, 2, 3, I'm going to be going down 1, right 1, down 1, right 1, down 1, right 1. But I only start doing that when my x value is greater than or equal to 1. So when I'm evaluating these, I will start by plugging in the most left and the most right. So when I do this, and I'm looking at green, the most left for green is going to be 1. The most right for green is going to be positive infinity. Now, since I can't actually plug in positive infinity and get a reasonable answer for graphing, I'm just going to follow it off to the right. For the red, the most left is going to be negative infinity, which I definitely don't want to plug in. So I'm going to just be sending that off to the left. But the most right ends up being 1. Now you may be saying, Mr. G, well, it can't actually be 1. Yeah, that's okay. That's why we do the open circle. So I'm still going to plug it in as if I were able to make it 1, but then just denoting an open circle means I'm not actually that exact thing. Here's graphing a step function. So step function is just a fancy way of saying that these things are going to overlap over the same point. So basically, this is like a tiered system of parking or anything else where you like pay for a certain like amount of time. So if I want to pay for parking, maybe it's like $1 an hour. So I pay my dollar. It doesn't matter whether I'm there for 1 second or 1 hour, it costs me $1. Then if I just even go 1 second into the next hour, I know the meter maid is going to be right there waiting to ticket me. So I need to pay $2 just to get that second hour. So this graph represents that. So if I pay the fee from my 0 to all the way up to 1 here, I get this rate, and this is just at 1. I mean, it's not exactly my example I just said, but it's pretty close. So from time 0 to time 1, not inclusive of the 1, it's just going to be 1. So that's where we get this red bucket right here. So I'm going to try and highlight these and end up writing over them for sure. So open dot right here. I'm trying. There we go. So this is just a graph, right? If I said graph f of x equals 1, you better be able to graph that. So in terms of what it looks like, just a horizontal line. The easiest graph we ever did in our lives, right? So f of x equals a number, just looks like this. This is the same thing as saying y equals 1. This is very different than if I wanted to say something like x equals 1. If I said x equals 1, it'd be a vertical line like that, but we already know that. So now let's continue coloring in a few of these buckets. So we'll do orange. Orange goes from here to here. Whoops, not. We'll do one more bucket here for green. So filled in. Lovely, lovely motor control here from Mr. G, as you can tell. And then lastly, we've got our blue, which will go to blue. There's the graph of this thing. So graphing this step function here is just going to look like this below. For writing a piecewise function, this gets a little bit tricky, but it's not too bad. The only thing different than what we've done before for writing an actual like function is it's going to stop somewhere. So if I told you, you have these 2 points, you got -2, 0, and you got 0, 2, and I said come up with an equation for it, you should absolutely be able to come up with an equation for it. So the equation for this one is going to end up looking like x plus 2. And we covered before how we find that equation. So we got to find our slope, then we're going to solve for our b value, and then we have our equation. So again, slope, plug one of these back in, solve for a b value, and we're good to go. This happens to have been given to us because we have this 0.02. It's not always that we're going to have the b value given, but it was pretty nice it was given on this one. So here we go, find the slope, find the b value. We got that, now we got our equation. So the only thing different about this piecewise function here is that it's not going to be the full line. So as I'm looking at this thing, it's going to be broken up into 2. The first part that I've got here in red is going to look like x plus 2, but it's only going to be, whoops, not x plus x plus 2, but that is conditional. We got if. So where does this happen? This happens from -infinity. Oops, I don't know if I'm going to run out of space here. I'm going to try and scoot things over just a smidge. So if my x value here is going to be greater than -infinity, but less than 0. So here I'm going to say x is less than 0. Now again, it's not less than or equal to because this is an open circle right there. For the next one, I again want to figure out what my equation is. So using these 2 points to generate an equation, I'm able to figure out that I get y equals x as my equation. Again, I'm not graphing y equals x everywhere. I'm graphing f of x equals x only if my x value is greater than or equal to 0. So now we have our piecewise function for this graph here. Solid dot coming from the greater than or equal to. Here we have a step function just like actually using one. So here we have $3 per half hour. There's the $8 max for 12 hours. So basically what's happening here, I'm just going to kind of explain this one briefly because we're not going to do a ton like this, but it's good to know, is that as we're going through, it's $3 per half hour. So for the first half hour here, it's going to be charged at $3. That's where we get this right here, right? We don't get charged at time 0, but anything past that we get charged. So ending here, open circle right there. For the next half hour, again, we're going to have to pay another $3 up to that point there. But then we hit this cap. So we hit a cap. Once we go past our 1 hour, so if we were to do 1.5 hours, 1.5 is our third half hour times 3 would be $9. Well, we don't pay $9. Instead, there's an $8 max for 12 hours. So here's where now I get this open circle here, and we get our horizontal line out to 12. So in terms of what this looks like as a piecewise function, it would look like this. $3 from 0 to 1/2, $6 from 1/2 to 1, and $8 from 1 to 12. In terms of using a piecewise function, this will be where piecewise functions are probably the most useful for you, other than like once you start understanding like how we have a tiered tax system and how that all works, is when you think about overtime and think about working. So when you're thinking about overtime and you're thinking about how much you're going to make at the end of a week, know that the first rate you get paid is your standard pay. So I'm going to try and highlight the fact that this slope is different than this slope. So we see obviously if they were the same, they would continue just in a line together. But there's a difference, right? So once we hit 40 hours, now we get paid 1.5 times what we normally would. So if our normal pay was 7 times 1.5 can make us $10.50 an hour. So now I'm looking at this of the slope of $10.50, and this is the slope of 7. But we don't just start at 0 here, right? We don't just lose everything we made once we get to that point. We start where we left off. So when we're doing overtime, we have all of our standard pay that piles up, and then it switches and kicks into high gear when we start making that time and a half. So to figure that out, I'd want to figure out, well, what do I make at 40 hours? So here's where I'm looking at 7 times 40 equals 280, right? So this is going to actually start and stop at 40, 280. So the first part, I would say this is my green. Actually, well, I did it in red originally, so I'll say red. And then here we got our orange. Just understand like the green overlaps the two of them. So like that's where we figure out this 280 value is coming from. So when we want to plug this value in going forward, there's a couple ways we can do it. Easiest way is to then just take the new value as a point. And so we're going to use 40, 280. And we're going to use this in our new equation where our m is 10.5. So just like the ones that we did before, we're going to plug that in. We end up getting to the point where our y is equal to 10.5 times t. So I'm just going to write x because my t's look like pluses, and minus 140. And you may think, oh my gosh, like why is this minus 140 there? That's crazy. Well, it's because we're adjusting for the fact that the first 40 hours were not worked at $10.50 an hour. They were worked at $7 an hour. So we're basically taking that chunk off. So as soon as I start plugging in values, 40 or greater, this will line up and fit. So just to wrap this whole problem up, it says how much we get paid if you work 45 hours. We're going to get 40 at the original rate and then 5 at the new rate. So basically, we're going to take that 45, plug it into this equation here, and we end up making $332.50. Last bit here for today is absolute value functions. We're cranking through this stuff. So absolute value functions basically is the graph for the work we were doing the other day. And these things look like these. my original v looks like this. This is just like y equals absolute value of x. And the reason it looks like a v is if I go 1 to the right and plug that in, the absolute value of 1 is 1. If I go 1 to the left, so I'm plugging in -1, absolute value of -1 is 1. So this thing ends up in the same spot both here and here. So that's how we get this v-looking shape from our absolute values. Now there are some pieces that shift this thing around. You can think about it like it was a piecewise function, although I don't know a single individual who is helpful to think about it that way. Maybe you're the one, who knows? The thing I do want to point out is that that point right there is referred to as the vertex, right? So where these two things meet together, you can think about them as two rays, just to jog back like a geometry term there. Where those two meet together is the vertex, okay? It's the center of this graph, and we have this axis of symmetry that comes down through. So my axis of symmetry is going to look like x equals, I'm going to say, my h value. Now, we don't understand what the h value is yet, but I promise we will get there. So as we're looking at this, just know that we have an x running, excuse me, x equals blah running through the center of our graph here. So if I told you the vertex was 2, 7, then the axis of symmetry would be x equals 2, because it's the same. Here is an example of a translation. So here we're looking at 2, absolute value of x minus 4, and then we get plus 3. The 2 on the outside is the a value. Probably going to scoot this down so we can get this explanation in with it, but I'll just jot this down first. H value is the opposite of what this looks like. So it looks like a -4. The h value is actually a positive 4 because it's x minus h. Again, we'll get to that in 1 second. My k value, which is the vertical thing at the end, equals 3. So I'm going to take this stuff and just drag it down a smidge. We're going to clean up our mess here. Poof. Here is my explanation for these things. So when we're looking at absolute value functions, it takes this form, y equals a times the absolute value of x minus h. And you can have multiple x's in here, like 2x, 3x, whatever, but we're not going to do anything crazy like that. And then we got plus k on the outside. The vertex of this thing lies at hk. Now, when we're looking at the h value, it's always opposite what it looks like, right? If it's x minus 3, the actual h value is 3. A controls whether this thing is going to open up or down. It says curve. It should just say opens. That's because I use the same explanation for parabola. So if you understand these, you understand parabolas. So A opens it up or down. If A is positive, it's up. If it's negative, it opens down. We have a minimum value if it is going to open up, and we have a maximum value if it's going to open down. So in this example here, we have a minimum, and it's the y value right there. The A also stretches this thing. So here we have an A of 2. It's going to narrow. So we see this is our parent function, the original, just x, or excuse me, absolute value of x. And as soon as we see this one here, we see this is much steeper. That's because it's 2 times and then whatever else is going on. So let's do this h value in orange here. So the h value indicates the horizontal shift. So now I'm talking about this one here. If it looks like x plus a number, it's going to shift to the left that many units. So if it looks like the absolute value of x plus 2, my actual h value is -2. And it's going to go left 2. Okay? So in this example here, when we're looking at it, we have an h value of 4. Right? It looks like x minus 4. So my h value is actually the opposite of that. It's 4. So that's how we get shifted 4 to the right. Again, this is 4 to the right. Actually, I'm going to do that right here. There we got 4 to the right. And then I'm looking at the k value next. So for my k value, this indicates the vertical shift. So for my vertical shift, this is easier. If it looks like plus a number at the end, it's going to go up that many. If it looks like minus a number at the end, then it's going to go down that many. Keep in mind, if I don't see an H or a K, it just means that they are 0, and that's totally fine. So in this example, I'll do X, and we'll say plus 3. The K value is just equal to 3, and we are simply going to go up 3. So in this example here, that's what's generating that part of the graph. So again, the A is a little bit trickier to represent, like showing you, but this was a much more gradual slope. This is much steeper. Axis of symmetry is X equals H. So now the comment that I made before hopefully makes sense. So again, we're running right through wherever this thing got shifted to. So if it got shifted to the left, obviously our axis of symmetry is going to shift to the left, and vice versa if it were shifted to the right. Here is a nice little summary as well of these rules, just in a slightly different format. Says the exact same thing. Here we have a graph and absolute value function problem. So here we notice our A value is -1. That means this thing is going to open down, and it has no stretch. So since the value is 1, when we look at the notes up here, the A value, it's the absolute value of this thing. Okay, so I don't care if it's positive or negative, I just care about the absolute value. So if it is negative, it opens down. If it is positive, it opens up. But the stretch on it, the 1 here, doesn't change. So if this thing were flipped up or down, and this A value is just 1 or -1, there's no stretch. If it were 2 or 1/2, then there would be a stretch. So I'm going to say this thing opens down, and I'm going to say normal. The next bit that I want to look at here is the H value. My H is going to look opposite from what it really is, because this is X minus H. If X minus H looks like X plus 2, what is my H value? Well, let's subtract X from both sides. Now we see that -H equals 2. Divide both sides by -1. H equals -2. So again, just showing you the math there of why it is opposite. So here my H value is -2. What that means is I'm going to shift to the left 2. There we go. Last one here is we'll talk about the K value. So for the K value, we're seeing it is +3, and the K value is nice. It's very straightforward. K value equals 3. So we're going to go up 3. So my vertex is going to take a little journey, okay? It's going to take a journey 2 to the left, and then up 3 relative to its original position. And that's how we get a vertex sitting right here. Now from there, what do I do? Again, know that this thing is going to be opening down. So my slope here for this left side is going to be X equals 1. And this one should be M value is 1. And here it's going to be M value is -1. So it is reverse on the opposite side. So when we're looking at this, it's always going to be down 1, right 1, down 1, right 1, and down 1, left 1, down 1, left 1. If this were a different slope, say for example is -2, I'd be going down 2, right 1, down 2, right 1, and left 1, down 2, left 1, down 2. So as we're doing these things, we'll see some kind of different examples like that, but it's consistent. Here we want to write an absolute value function. To do that, we want to first take note of where the vertex is. So I look at this thing here. That vertex is HK. So I know my H and K values. My H is 0. My K is -3. So when I'm looking at this, I want to say, okay, well, I know that I've got Y is equal to A X minus H plus K. So when I'm doing this, I already know my H and K value. That's good. I just need my A value. So to find the A value, I need the slope between these things. So it looks like I'm going up 1, 2, 3, 4, and to the right 2. So my slope here, I'm just going to highlight it using these 2 points, is 4/2. And you can set it up in the full formula if you want. It looks like -3 minus 1 all divided by 0 minus 2. So we can also, go the other direction. 1 minus -3 over 2 minus 0. So we get to the point where it looks like 4 over 2, which will simplify to just 2. Now I know my m and my slope for this thing is the a value. Again, if it's positive, it's opening up. Negative, it's opening down. So my a value is 2. So now I'm able to fill this thing in. So now I can say y is equal to fill in the values. So here we have, I'm going to write out plus 0 here, but you never actually do this. It would just look like x. I'm going to write out the final answer in a second. Here I get plus -3. Again, we don't typically write that. And then I'm going to throw my 2 out in front. In terms of a simplified answer that I'd be looking for, it should look like y equals 2x and minus 3. And we are good to go. Interpreting absolute value functions. So this is a little bit of an abstract problem. I don't love this one, but I don't hate it either. So I'll mention it quickly, and then that is it for today. So looking at this one here, we have a model for an absolute value function. So we see that this thing is going to be opening down. It's going to be shifted to the right and shifted up. So here we see shifted to the right, it's shifted up, and yes, for sure, it's opening down, okay? So it says graph the function. Cool, we did that. We learned how to do that a second ago. And now we want to interpret the domain and range. So in terms of domain and range, domain is my x values. Range is my y values. So the domain for this thing can go from 0 to 5. And the reason it can go from 0 to 5 is that that is where the tent stakes hit the ground. We're assuming that this thing is not going to be buried into the soil. Then for my y range, you see the height of this thing goes from 0 on the ground up to, and this hit a peak at 3.5. So my y values will be 0 less than equal to 3.5. That would be my domain and range on this problem. And we will wrap up the recording here and I'll answer questions.